So when we talk about consistency versus availability in distributed systems, it really comes down to understanding the CAP theorem. You know, you can't have all three, consistency, availability, partition tolerance, at the same time.
But doesn't choosing consistency mean sacrificing some reliability?
Absolutely. But it depends on your use case. If you're dealing with financial transactions or something where accuracy is critical, then you prioritize strong consistency over high availability. Otherwise, a small outage might cause major issues. And let's be real, no one wants their bank account showing negative balances because of inconsistent reads.
What if there's a way to balance both without compromising too much on either side? I feel like there should be middle ground somewhere.
There is. And that's where eventual consistency comes into play. It's a compromise. In an eventually consistent system, you allow for temporary inconsistencies, but ensure they get resolved over time. This approach sacrifices immediate consistency for higher availability. Imagine posting updates on social media. Sometimes your friends see them later than others due to replication delays.
That makes sense, but how do we determine which model works best for our project?
Well, first identify what your users need most. Is it crucial that every operation completes successfully and immediately reflects across all nodes? Or can you tolerate brief periods of inconsistency for the sake of keeping services up during network partitions? It also ties into how your data will be used. Transactional integrity might require stronger consistency guarantees compared to content management systems where eventual consistency could suffice.
I guess understanding user expectations and operational needs is key then.
Exactly. Plus, don't forget about the trade-offs in terms of complexity and performance overhead associated with maintaining stricter consistency models. They often involve more complex algorithms and higher latency penalties.
Makes me wonder how other companies handle these decisions.
Yeah, understanding how other companies handle these decisions can give us valuable insights. But first, let's make sure we're solid on the fundamentals of the CAP theorem itself.
Sure, I remember the basics, but a refresher never hurt.
Right. The CAP theorem states that in any distributed system, you can only have at most 2 out of 3 properties: consistency, availability, and partition tolerance. Partition tolerance is essentially non-negotiable for any practical system operating over a network, so the real choice is between consistency and availability.
So if partition tolerance is always necessary, does that mean we always have to choose between consistency and availability?
Exactly. And this has huge implications for system design. For example, Amazon's Dynamo was designed with high availability in mind, even at the cost of some consistency. On the flip side, Google's Big Table prioritizes strong consistency over absolute availability.
That makes sense. So depending on our goals, we pick what matters more.
Precisely. And it's worth noting that these choices aren't just theoretical. They directly impact user experience and business outcomes. A highly available service might be slightly inconsistent at times, but users may not notice or care as much as they would about downtime.
It sounds like finding the right balance is crucial.
Definitely. Balancing these trade-offs requires careful consideration of your specific context and requirements. We need to think deeply about what our end users expect and what kind of compromises they can tolerate. Exactly. Now, let's talk about strategies for maintaining consistency in microservices architectures. It's a bit more nuanced since each microservice can operate independently, but still needs to maintain coherence with others.
That sounds challenging. Are there any specific techniques that work well?
Definitely. One common approach is using distributed transactions, like the saga pattern. Instead of having a single transaction span multiple services, you break it into smaller, compensating transactions. Each step can be rolled back if something goes wrong later on.
So it's like a series of small steps that can correct themselves if needed.
Exactly. Another technique is event sourcing, where you store a sequence of events rather than just the current state. This allows you to reconstruct the state at any point, and ensures that all services have a consistent view of history.
Interesting. Does this mean we need to keep track of every change?
Yes, but it provides a robust way to ensure consistency, and also gives you an audit trail. Plus, you can replay events to recover from failures or reconcile inconsistencies between services.
That seems quite powerful, but also complex.
It definitely adds complexity, but it's often worth it for systems where consistency is critical. You also need to consider how these strategies affect performance and scalability. For example, ensuring strong consistency might introduce latency as services wait for confirmations from others.
It feels like there are many factors to balance here.
Absolutely. And remember, no one-size-fits-all solution exists. The right strategy depends on your specific requirements and constraints. Agreed. Now, let's shift gears a bit and talk about implementing eventual consistency patterns in NoSQL databases. This is particularly relevant given the distributed nature of many NoSQL solutions.
That sounds like a good transition. What are some common patterns for achieving eventual consistency?
One widely used pattern is the use of timestamps or version numbers to manage updates. When data is replicated across nodes, the node with the latest timestamp takes precedence. This helps resolve conflicts and ensures that eventually, all nodes converge on the same state.
So it's like each update has a timestamp to decide which one wins.
Exactly. Another pattern involves conflict resolution strategies, such as last write wins, LDWW, or operational transformation, OTT. LDW simply picks the most recent write, while OT tries to merge changes in a way that preserves intent.
Last write win seems straightforward but could lead to unexpected results, right?
It can, especially if there are concurrent updates happening simultaneously across different nodes. However, in scenarios where slight inconsistencies are acceptable, and you need high availability, LDW is often a pragmatic choice.
I see. What about handling conflicts more intelligently?
Operational transformation can be more sophisticated, but also more complex. It involves tracking operations rather than just values, allowing for intelligent merging of conflicting updates based on their sequence and intent.
That sounds like it would add significant overhead.
It does come with additional complexity and computational cost, but it offers better guarantees on preserving user intent and avoiding loss of data during merges.
It's interesting how these patterns balance between simplicity and robustness.
Indeed, the key is understanding your application's needs and choosing the right level of consistency that aligns with those needs.